Welcome back to Physics 142. In this video, I want to talk about the energy that is stored in an inductor. And to do that, I first want to think about other circuit elements that store energy. And you might recall that the main circuit element that we've had so far for storing energy is a capacitor, right? And we wrote down earlier in the semester that the energy that's stored in a capacitor either depends on the amount of charge you're putting on the capacitor. We said Q squared over 2 times the capacitance. Or another way we wrote it is 1/2 times the capacitance times the potential across the capacitor squared. All right, 1/2 CV squared. That ended up being how we could calculate the energy that was stored in a capacitor. All right. Now, another way that we like to think about sort of input energy into a system, right, is we often think about the power, all right, and we say that, you know, the power that's sort of put into a system, maybe from a power supply, we realize that our formula for power from a power supply was that it's your current times your potential, all right, that the amount of power, sort of how quickly you're putting in that energy is current times potential. All right, so capacitors were storing energy and power supplies could put it in, all right, with V times I. So now inductors also, it turns out, can store energy. And the way that this works is if you want to get current flowing in an inductor, all right, if you want to make some current flow through all those loops in an inductor, well, inductors don't want current to flow through them, right? They want to stay right where they are. They want to stay, you know, initially at zero current. And so if you want to get some current flowing, it's going to take some energy to get that current flowing in the inductor, right? You're going to have to put some energy in to get that current flowing. And so, well, how much, right? So I guess, you know, maybe we should write that down, right? Establishing current in an inductor requires an input of energy. All right, well, how much? Well, the way that we can calculate this, all right, sort of one way that I know how to calculate this is, let's say that the stored energy in the inductor, we'll call that U, right? It's kind of the potential energy of the inductor, if you will, right? How much energy we're storing, all right? And, well, U, what's the relationship between U and P? Well, the power is how that stored energy changes with time, right? So U here is the stored energy, right? And power is du dt, how that changes with time. So if I wanted to calculate U, then I would take the integral of power times dt, right? I multiply a dt over here, right? And I would then integrate all the du's, and I would get that U is the integral of power times dt, all right? But power, well, power, we know that power is V times I, right? Potential times I, or a lot of times for potential, we've been talking more recently about EMF, right? They're the same thing, or close to the same thing, right? So for power, I'm going to write EMF times I dt, all right? But now, well, the EMF for an inductor, all right, we've written that down already. The EMF for an inductor, all right, is going to be L times di dt, right? L times di dt. And since the minus sign is just dealing with the opposition, all right, I will drop it here for just a second. It just matters, you know, it's just the order of how we do the integral, right? The limits of integration. So let's just write the integral of L di dt times dt, all right? Times I. There still is an I here, right? So let's maybe write that times I dt. There we go. All right. Well, now I have two dt's, and so they can basically cancel those, right? It's just a little bit of time, those cancel out. And so now I just have the integral of L di times I. L is a constant. It can come out of the integral, right? And so what's the integral? So, you know, this is the L times the integral of I di. And, well, what's L times the integral of I, what's the integral of I ди? Well, that's going to be 1/2 I squared, right? That's the integral of I. So we can just write, ultimately, that the energy that's stored in an inductor, all right, in an inductor, ends up being 1/2 times L times the current squared. All right, that's the energy stored in an inductor. And you'll note this looks a lot like a capacitor, right? For a capacitor, it's 1/2 times the capacitance times the potential squared, right? Here it's the current squared. So, the energy actually comes from the fact that you have current, all right? And that means ultimately that the energy is stored in a magnetic field. Right here, right, you have potential. The potential meant you had an electric field going in between those two plates, right? For a capacitor, we had, whatever, I'll do it in black, right? For a capacitor, we had some electric field between those two plates, right? And the potential sort of quantified our walk through that field, right? For an inductor, we've got current flowing, and so that means you're going to have some sort of magnetic field, all right, some magnetic field in that inductor, and that is actually where your energy is going to be stored. And so we'll think a little bit more about this in future videos, but wanted to get this formula written down, and I think it's sort of a really interesting parallel, all right? Inductors are storing energy by having current flowing through them, whereas capacitors are storing energy by just building up charges and just having it sit statically there. All right, so, and we'll think about how these interact with each other in future videos.